Today we're covering lessons 13 and 14 in Unit 6, Introduction to Exponential Functions. We're going to be looking at graphs, Part 1. Turn to page 262 and complete the warm-up. Jada received a gift of $180. In the first week, she spent a third of the gift money. She continues spending a third of what is left each week thereafter. Which equation best represents the amount of gift money, we're going to call that G, in dollars she has after T weeks? Be prepared to explain your reasoning. All right, get an idea of what this is about. Now let's highlight numerical data or numerical information. We have a gift of $180 that Jada received. Okay, she spent a third. She continues spending a third each week thereafter. All right, now we want to write the equation that best represents that. So let's try to write the equation without looking at the answers to guide us. All right, so we're going to use, let me go ahead and highlight the variables. We're going to use G for gift money and T for time, the amount of weeks. All right, so we're going to say G is equal to the initial amount, 180, times the growth factor, in this case decay factor, because she's spending money, so she's going to be losing money. She spends a third of the gift money, so we've got to take that 1/3 and we've got to subtract it from 1. So 1 minus 1/3 is equal to 2/3. This is going to be our growth factor, in this case decay, that goes right here in our equation. So 180, she spends a third, so we'll have 2/3 left. Multiply those amounts together and then raise it to the power of t. Now if we were looking at this in terms of x and y is going to be our outcome and t is going to be time. T is time, which is x. So we could replace G with y and t with x. But we were told to use those variables. Let's see if we can find a match. It's not going to be 180 minus. We can go ahead and eliminate that. That's not exponential growth or decay. It is going to be 180 times 1/3 to the t, except 1/3 is what we're taking away. 2/3 is what we have left. So that's out. This is often what we get confused with. All right, now we don't start with 1/3. We start with 180. So this is out. And let's just go to the last one and check to see if we have a match here. 180 is our initial amount. 2/3 is our growth or decay factor, raised to the power of t. So it's going to be d. Remember, the fraction for the equation is what remains, not what the amount is decreased by. All right, turn to page 261, Activity 1, Equations and their graphs. Each of the following functions, f, g, h, and j, represents the value of an investment in a different company in dollars as a function of time in years. They're each written in the form of m of x equals a times b to the x. Remember, a is the initial amount, b is your growth factor, x is our input, and it's going to be our time. X is always time. So use graphing technology to graph each function on the same coordinate plane and check your predictions. So put these equations just like they are on 4 separate lines in Desmos. Use Desmos.com, or if you have a graphing calculator, you can use that as well. We're using Desmos in Math 1. Alright, once you put those in, you'll have different color codes depending on what your computer gave you. Now let's look at what f of x equals 50 times 2 to the x looks like. That's going to be the red line, this one right here. So it starts out here, we start with 50, we're doubling it each time. Then g of x, we start out with 50, and then we're going to triple it each time. So that's going to be our blue line. H of x, we start out with 50, and then we multiply it by 3 halves. 3 halves is 1.5, so we're going to increase it or multiply by 1.5 each time. That's going to be our green line. Doesn't go up as quickly as these do when they start rising. And then the purple line is going to be 50 times 1/2. So that's why this one goes down. Okay, it's decreasing. These are increasing. All right, when b, this value here, is larger than 1, the values of b mean the function grows more quickly as x increases. Okay, so look at 2. 2 is going to be the red one. 3 is going to be the blue one. And 1.5, when we multiply by 1.5, is the green one. So the function is going to grow more quickly as x increases. Now a positive value of b that is less than 1 means the function is decreasing. So it's going to start high and it's going to drop down and approach 0. All right, now take these functions, these equations of functions p, q, and r. They're also written in the form of m times x equals, or m of x, the input is x, equals a times b to the x. A is the initial amount, b is the growth factor, and x is the exponent, and it's going to be our time. With your partner, make a prediction about what will be the same and what will be different about the graphs of the 3 functions. If you're doing this at home by yourself, you're not going to have a partner, so try to think through this on your own. But if you're at school, doing this at school, stop and talk to your partner and discuss. What's going to happen when we put this function in? What's going to happen? What do you think is going to happen to the equation when we put this function in? Our initial amount is going to change. Previously we looked at the growth factor changing. This time we're looking at the initial amount, but the growth factor's staying the same. We're quadrupling each time. So predict what you think that graph is going to look like. Then put these equations into Desmos. You should have 3 of them just like this. Stop for a minute, get that done, come back and compare. Alright, this is what the graph looks like. Okay, the first one, when we start with an initial amount of 10, okay, it's going to start here. Okay, and it's going to go up from there. Okay, we start with Q. That's going to be the blue line. So that's going to start up higher at 40. And then of course the green one's going to start up at 100. It's going to increase from there. So maybe I'm not looking at the right quadrant. Take a look at what yours looks like in Desmos. Did your prediction match what actually happened? All right, write down in words what happens. Changing the value of A, the initial amount, shifts the graph up. So each of these graphs is going to shift up. It's going to change where we start. The first one starts at 10. Second one, the initial amount, the y-intercept is 40. And the third one, the y-intercept is 100. Okay, if we go less, it's going to go down. The higher it goes up. It just shifts this up. Turn to page 265. Activity 2, graphs representing exponential decay. All right, so now we have the same initial amount, and our growth factor, these are numbers less than 1. All of them are less than 1, so it's going to show decay. Now it looks like they're changing at different steepnesses, dropping at different rates. Okay, so what do you think 1/4 is? Make a prediction or put your equations into Desmos and compare. Looking at function 1, function M, that's going to match with D. Say 1/4 is going to drop this way. And then we're going to go to 1/2. 1/2, our decay factor is 1/2, so we have 1/2 remaining. Start with 200. And we go down to 100. That's going to be C. And then 3/4 is going to be B, and then 7/8 is going to be A. This is the smallest one, so it's going to drop quicker. This is the next smallest, so it's going to drop the next quickest. The 3/4 is the next in order, so it goes here. And the 7/8 is closer to 1. So remember, 1 would be like a straight line, but this is going to drop less quickly. Let's take a minute to look at that. Now let's put that into words. The functions are all exponential and the bases are all less than 1. So the graphs will be decreasing. The most rapidly decreasing will be the one with the smallest base, and the least rapidly decreasing will be the one with the largest base. Now turn to page 265. We have functions f and g defined by these two equations. F of x equals 1,000 times 1/10 to the x, and g of x equals 1,000 times 9/10 to the x. Which function decays more quickly? Do you remember what we just saw? Is it the smaller fraction that drops quickest, or the larger fraction that drops quickest? So turn back if you need to look, pause the video, and then complete your answer, and then compare the answer with mine. All right, when we multiply, we start with 1,000, and then our decay factor is 1/10. 1/10 is smaller than 9/10. This has a smaller base than 9/10. Both of these bases are less than 1, so both decrease, but the 1/10, the smaller fraction, decreases more rapidly. Use graphing technology, put both of these functions into Desmos, and verify your answer. Check to see if your graphs look like this. Okay, the initial amount, the y-intercept is 1,000. The red line is going to be the growth factor, or in this case the decay factor of 1/10. That's a lot smaller than 9/10. It's going to drop more quickly. All right, in the summary and glossary, get your highlighters out. Highlight this equation, Q of t. Take a look at that. It's going to start at 5,000. Okay, so look at your increments, 20,000, 40,000. So this is 5,000, 10,000, 15,000, 20,000. So 5,000 is going to be right here. Each of these equations or functions, function Q, function P, and function R, start at 5,000. But let's look at the growth factor. Okay, this time we have a number greater than 1. Okay, so 1.5, that's Q of t. It's going to be that blue line. Each time we go up by 1, we're going to multiply the previous amount by 1.5 or 1.5. Okay, let's look at P of t. This time we're going to double it. So this is P. Okay, 2 is bigger than 1.5, so it's going to increase quicker. This time it's growth. It's a number greater than 1. So the bigger the number, the quicker it increases. Smaller the number, the slower it increases. So let's look at R. R is the smallest of those three growth factors. 1.2 is smaller than 1.5, and 1.5 is smaller than 2. All right, let's look at a word that we haven't talked about in this lesson, but you need to highlight it and you need to know it. We talk about end behavior of the functions. Okay, end behavior is describing the bacteria population. As time goes on, as we move in this direction on the x-axis, what is happening to each of those graphs? That's called your end behavior of a function. It's the characteristics that a function eventually takes on when its input becomes large enough. So what we want to know is, where are these numbers going? The larger we get out into infinity, what happens? All right, complete the cool down. Complete it in your workbook. It's not, the problem itself is not in your workbook, but you can copy it down somewhere in your workbook. And then transfer it into Canvas when it opens up. All right, we have 3 graphs representing 3 exponential functions, f, g, and h. Okay, f of x equals 10, initial amount, times 2 to the x. So we're going to be doubling this in every increment, every time we go up by 1 in terms of time. H of x starts with an initial amount of 20, and then we quadruple that with each increment. Which of the following could define the function g? Okay, so we've got f right here. We've got h. F is on the bottom, the red line. H is on the top, the green line. And g is the blue one. So first of all, where does g start? The initial amount is the same as h, and h starts at 20. So we're going to eliminate equation C, because this starts at 10. It could be equation A, B, or D, because they all start at 20, just like h of x does. Okay, now h of x is increasing by 4. That's going to be this green one. And then f of x is increasing by 2. It starts slower, but it rises slower. Okay, so it's going to increase, that growth factor is going to be a number between 2 and 4. So it can't be A, because the growth factor is less than 2. And it can't be D, because the growth factor is greater than 4. The only thing it could be, the growth factor between 2 and 4, is 2.5. All right, the graph of g has the same y-intercept as the graph of h. That's what we saw, which is 20. It grows more quickly than f, but more slowly than h, so the growth factor must be greater than 2 and less than 4. So you're asked to look at these carefully. All right, your practice that you need to do in your workbook and turn in through Canvas is page 267, questions 1 through 4. Also, don't forget your cool downs.